Anything else you want to clarify before
No.
we carry on?
No.
Okay, I think most of it you have learned before. It's not something new. It's just that you have to apply it, that's all. Let me just get the thing. Okay, let us carry on with what we have done. We are now looking at direction. We started with a current carrying conductor. As I said, just to refresh your memory, we are looking at three different types of conductors. Infinitely long wire carrying a current, a coil, a thin coil carrying a current, a solenoid carrying a current. So most of it are revision work for you, except that you have to know how to use a formula, that's all. That's something new. Right? Magnetic field lines or lines of force can be drawn around a current carrying conductor. Direction of field lines depends on direction of current. Direction of lines of force can be found using, don't bother about Maxwell's screw rule. Right? This one is only those who drink or have to use a cork to open, then you can imagine it. If not, use your right hand curve rule. Right? Your right hand, this is your right hand. You just curve it around. The thumb represent the current. The fingers represent the direction of the field. Right? It's always circular. This one, okay. Right? Close together, further apart, further away. Sorry, too fast. Okay, thumb represent, sorry. Thumb represent direction of current. That's your thumb. Direction of the current. Okay, you curve your finger. So that represent the line of force. Right? And the direction is the pointing of the finger. How to derive it? Okay, suppose you have a wire. It carries a current I out of the page. That's your current carrying conductor. Remember, the dot can be represent a magnetic field coming out. But in this case, it tells you it's a current, so you have to take it as a current coming out. Right? That means you are looking from the top, current is coming out of the page. So the magnetic flux density is a perpendicular distance R from the wire. So given by Ampere's law, that one there, or you can use integral. Right? This one means parallel to this small elemental length. That's the permittivity of free space. Sorry, permeability of free space as your current. Okay, in this case, your B, remember we say is circular around that. So your delta L, you sum it up, it will be circular also. So it's 2 pi r. That's your length, 2 pi r, right? Parallel to the field. Then what is enclosed is your current I from the wire. So that is your perpendicular distance R distance. And you just, there's your B. You look at this point there, right? You remember the right hand curve rule. Okay, coming out of the page there. Okay, so it's anti-clockwise. That's your B. So at that point there is a tangent. So you want it in the same direction, so you have to resolve it parallel to the small length there, delta L. So that's your delta L. Okay, so you cross multiply, take your 2 pi r to the other side, that's how you get that. Okay with that? Any question? Yeah, just using Ampere's law. We don't want to use sum. Usually should be integration now. Yep. Any question?
No.
Okay, if not, let's carry on. That's how the narrow look like, right? We are looking at the side view. Right? That's the side. The side view here. You get a circle there. Radius r. Usually the wire is insulated. Right? It is not usually it can be deceiving because it looks like the color of copper, but it's actually you cannot have copper joined together. It has to be a thin layer of insulation. Okay, so that's the formula. You have to memorize it. Factors affecting the magnetic field strength, right? This is B at the center, right? B at the center. R, in this case, is the radius. N is the number of turns. I is the current passing through this flat coil there, or loop, right? Or a circular coil, or flat coil, or a loop. Right? So two ways we can increase the field strength. B, increase the current, all depend on current. Current, greater field. Increase the number of turns, right? Each turn will contribute to B. So N turns will contribute to N times of. Right? Remember, R is the radius, so we are looking at the field at the center there, not other part there, at the center there. So you make the loop becomes bigger because radius, and B at the center will be smaller. Right? Inversely proportional to R. Right? Learn to read the formula, memorize it and use it. Direction of field. Okay, there are various ways to look at it. To me, I just say use the same as the long wire. One thing to memorize only, one rule. Right? Your finger represent the current, the thumb represent your field. So it's more or less circular, but it's distorted. So that is what it looks like. If you look at this part, the current is going up. So you look at it, it's going to go anti-clockwise. You look at this part, the current is going down. Current is going down. Right? So it's clockwise. That's all. But it's your preference. This is your plane view. Usually they will ask you to draw plane view rather than three-dimensional because it's more difficult. Right? Center will be straight because they are adding up. Right? They never cross, they add up. So it won't be like this part, concentric circle, it will be distorted. Because at this part there, this part will be this one contribute by this wire. The current there will be anti-clockwise. Remember, this one will go that way, clockwise. So in a sense, it becomes weaker and weaker as you go further and further away. This part, they reinforce each other. Right? So look at the plane view and apply your right hand curve rule, like here. This part there, you get it anti-clockwise. This part, you get it clockwise. Or, right, as I said, your choice. As long as you can get the right direction. Right hand grip rule. Clasp the coil with your fingers. Hold on the neck. So in this case, it's this way. Grasp it. And then the finger, the thumb will represent the direction of the field. Okay. To me, this is easier to remember rather than all this unnecessary one. Okay, as long as you can get direction. This one is just extra knowledge for you. How we get uniform field. Right? The radius of the coil, flat coil, the same for the two coil. And the distance between the two coils is R. So the field in between them is constant, uniform field. Right? This is extra knowledge, just don't bother about it. We call it Helmholtz coin. Okay, solenoid. Let me just test you whether you can remember your SPM work. What is the polarity of A? Which part is north, which part is south? This one a bit harder to see. This one is coming out. Okay, coming out. Okay.
Which part is coming out? Which part is coming in?
This one is coming out. This one. This one is outside. That one is behind. This one is behind.
Oh, positive one coming out, negative one coming in.
This one is coming out. So you have to know the direction of the current.
But I don't understand why is it coming out.
So A is what? This part is what? North or south?
Oh, that's not lah.
Huh? Correct.
Not because from positive, but
This is a positive. There's a current going that way. Right? So it's going to go.
Current. Field is different.
The current. This part is going to be clockwise. Yeah?
Coming out lah.
So it should be north or south. Should be south, isn't it? Here. You have to review. Yeah? Same right here. Right? You should be able to know this is north. Right? This is anti-clockwise. Okay. So you go over there. You go over there. I just test you, see whether you can remember your SPM work.
Yeah, I learned solenoid before, but I forgot already.
Yeah, that's why I say forgot already all your SPM work. Give back to your teacher already. Okay, let's try to look at the solenoid. Right, several turns of wire in the form of a cylinder. When current flows through a solenoid, right, current is there. The magnetic field lines formed around the solenoid is the same as a bar magnet. Right? Same as a bar magnet. This one shouldn't be so close together. It should be further and further away. Right? That's why I say internet is free, but always remember, refer to your textbook. Except in the bar magnet, it doesn't go through the magnet itself. Right? But in the solenoid, it goes through, pass through. Right? That's your bar magnet. It doesn't go inside, only outside, that's all. Right? So it should be further and further apart like here. It shouldn't be that close together. Right? So you look at the solenoid and the field lines, you find that within here, right, within here, before the end there, they are all looks like they are parallel. So it means that they are uniform and constant. But as you go out, right, the field lines are spreading out. So this one they have been constrained. As if they can spread out into a bigger area. So we can expect that the field line becomes smaller and smaller as you go further and further away. Sorry, I pressed something wrong. Right, so inside there is parallel, so it's uniform. Right, as the line move outwards at the ends there, open end, normal constraint already. So the same number of lines spread over a bigger area, so it becomes non-uniform. Right, shown by not normal parallel. So uniform somewhere around here. Then it start to decrease. Non-uniform outside. Right, you compare the solenoid and the magnet. The field is stronger at the center and decreases to half at the ends and decrease further as it goes further and further away because it can spread over a bigger area. along this area, right? Becomes smaller. Half here, inside there is B, stronger at the center. Right? Magnet, it doesn't pass through the magnet, but the coil, it'll pass through. Right? There's a difference. For long solenoid, right? What do we mean by long solenoid? It means that the length is longer than this diameter. Okay? That's how we define a long solenoid. The length is longer than the diameter. Right? Or the length L is greater than your D. Right? That's your D. That's your length. Okay with that? There's a formula you need to memorize, you need to derive. Right? And then know how to read the formula. Magnetic field strength or field increases with increasing current, right? Greater current flow, greater field, greater number of turns, right? This is a number per unit length. And more turn, remember each turn will contribute to the field. N turn will contribute to N, but it becomes longer. So it becomes longer, the field becomes smaller also. And if you change that, that can be made of iron, then you have to mu R. Right? This permeability of free space, number of turns per unit volume, current flowing in the solenoid. That's how the graph will look like. Right? Towards the center here, constant, largest B naught or BC. And then at the end here, it becomes half BC over 2. And as you go further and further, the field decreases, becomes smaller and smaller, comes 0 at far away. How to determine the polarity? I think this is the easiest rather than look at the clockwise or anti-clockwise, but it's your choice. Which one you prefer? Right? Basically, this one you use your right hand. Right? Just grip the solenoid. Fingers represent the current. The thumb represent direction of the north. Right? So we call it right hand grip rule. Right? Just imagine your right hand gripping the coil of the solenoid. The fingers represent the direction of the current. Your thumb will point to the direction of the north pole or direction of the field, B. Okay with that? Any comment? Anything that is not clear? Okay, can or not?
This one is now right hand grip rule lah.
Grip rule, right hand grip rule. As long as you know how to use it, it doesn't matter what you call it. Just use your right hand there. Just grip it. Grip the solenoid. The fingers represent the current, direction of the current. Your thumb will tell you the direction of the field B. So it's pointing to the north. So that part is your north. That's your thumb. Represent that. That's your fingers. Represent the direction of the current. This one is easier. Right? Or if you prefer this way, you look at the end there.
Oh yeah. The what's that? The current will go
you
to
look
the
at the current,
solenoid, and then the
current.
field is north and south lah.
So if it's anti-clockwise, it's north. If you look at the end there, it's clockwise, it's south.
Now I remember.
Right? This one is up to you, whichever is easier to use. To me, I feel your right hand grip rule is easier. As long as you can get direction, good enough. Okay? North, if it's anti-clockwise, if it's clockwise like that, then it's south.
Yeah.
And still remember I studied this in Form 3. What is a top? Right? Just imagine that your stick there, very thin stick there, you use a string to constrain it, they will be all parallel. But at the end there, where there's no constraint, you can see that they spread out a bigger area. Same with your solenoid. Right? So if it's a long solenoid, the length is greater than the radius. So we can increase the magnetic field. Right? Example in electromagnet, can use iron, steel, cobalt, nickel, which we call it ferromagnetic material. You place it in the solenoid, it will increase the electromagnet. Right? So we just modify by using mu R. Mu R. Mu R is for iron or steel, whatever we use. It's a constant known as relative permittivity of material. Right? Syllabus doesn't mention anything about that. So maybe this is extra. Right? We solve iron, you can see the increase by 5,000 times. It's in your book. Nickel and cobalt is about 10,000 times. Right? That's why we use electromagnet. Can separate the ferromagnetic material from the insulator for non-ferromagnetic material. Okay, so we have more or less completed it. We do some example, and we call it a day. Right, so magnetic field, we have ferromagnetic material, iron, steel, cobalt, copper. Right, placed in solenoid, what does it do? It concentrate. Concentrate means increase the field strength, magnetic field strength. Used in electromagnet, electric motor, where you want to separate the metal part and the non-metal part. Right? It can be magnetized. Ferromagnetic material can be magnetized. So with steel, you use steel, you magnetize it in a coil of wire, it becomes a permanent magnet. It means you cannot remove the magnetism, will stay there. Iron, temporary magnet. That means as long as the current is flowing, it is a strong magnet. You switch off the current, it loses its magnetism. Right? That's why we call it soft magnetic material. Non-ferro material will be example, be aluminum and copper. Cannot be magnetized in magnetic field. Right? That's why it's non-ferromagnetic. Okay, let's just do an example. What is the polarity of the solenoid? Your left-hand side? What's the polarity? Yep. What's the polarity? Why so long? Right? What's polarity of the left-hand side? This side. I've given you the rule. Yeah.
Wait, Achan. This is anti-clockwise, right? Yeah, it is anti-clockwise.
You're supposed to be able to read that yourself. Clockwise or anti-clockwise?
This is anti-clockwise, so the right-hand side is not lah.
Right-hand side is this side.
Yeah, north, and then the other one is south.
Are you sure?
This is anti-clockwise one.
This part is anti-clockwise, man. You look carefully. So I just show you the answer. Use your right-hand grid rule easier. This is clockwise, that's why you see you can misread it. Clockwise or anti-clockwise, a bit of imagination there. You have to look at this end there. It looks like it's clockwise, it's going that way. It's going in, so it's clockwise. Your thumb, using this grid rule easier. Right? Your fingers there represent this direction. The thumb pointing to the direction of B. That means this is your north. The thumb pointing to the north. Okay?
Oh. So if
Okay,
the
now go
thumb
and count
pointing
for
to the
me.
other side, no. If the thumb pointing to the other side means it's not lah.
If it's pointing to this side, then this side will be north.
Oh.
Right? That means the B is going into a straight arrow is going straight line from right to left. That's your north. Okay, calculate for me your number per unit volume. Sorry, your small n, number per unit length. How to calculate that? Go and count. Imagine this is one loop there.
What do you want me to count again, sir?
What is your small n, number per unit length?
Small n.
Yeah, small n. This one? That's small n. Number of turns per unit length. Okay. Yeah. Count number of turns there or number of loop there. Then divide by L. Can or not? Yeah, 16, isn't it? Wait, count. That should be 16 turns there. Consider
Yeah,
everything as one turn
16.
there. 16 divided by length. That's how you find your small n, the n there. Right? Make sure you do your checkpoint. 16.4.
You finish the whole subtopic, sir.
Yeah, almost finished already. Going to do some example
Oh, almost.
to make sure you know how to apply what I just teach you. If not, it's a waste. If you want to go too fast, it's no point. Go fast already and then you get lost. Better that you understand and got time to solve your question. That's how I can see progress. Go too fast, you will get lost.
Okay.
That's why I'm slowing down. No more letting you telling me what to do. Okay? Teaching you one or two topics. Right? That's how we can do the experiment. Right? There's your hot prop. There's your solenoid. Okay, we'll be finishing in 10 minutes time. So I will complete also. Okay, so these are the extra formula that we learned. So all this formula you have to learn to do it. I want to summarize for you the formulas that we have current carrying conductor. What is your mu naught? Then there is your narrow circular coil or loop. Then we come to solenoid. What the field looks like. Right hand grip rule. Okay. Try this number one. 4 parallel conductors carrying equal current pass vertically through the 4 corners of the square W, X, Y, Z. In 2 conductors, the current is flowing into the page, and in the other 2, out of the page. What is the direction of the current in order to produce a resultant magnetic field in the direction shown at O? You want the resultant field to be in this direction. So what is the answer? Right? This is a plane view. You look from the top there. Imagine there are 2 of them coming out, 2 of them going into the page, the current. And you want a resultant magnetic field in this direction at the center there. And it's a square. So what's your answer? Yep. You probably have to take another 10 more minutes and then new Zoom.
So I thought 1 hour. What?
I know 1 hour. It's just that I need to make sure you understand first before I start this topic, because you're supposed to do your homework. Yep, what's the answer? Can or not? Use your right hand. Yeah, you're just applying that one there. Applying this rule for each of the wire.
Oh, okay. Back to the question, sir.
Yeah, given you already here. Right? Current coming out. There's your field. You look at this point, it's a tangent. Look at this point, there's a tangent. Same here. At this point is a tangent. At this point is a tangent. So this one is anti-clockwise.
No, but how you know, sir?
That's why I say you have to look at each of them and see which is the best answer.
Oh, trial and error.
Yeah. There's no shortcut. Okay, so if you take this one as going in, right, then use your right hand.
What is going in? Current going in.
You just imagine it's going in, and then try it.
No. Current going in, is it?
Current going in. There's a cross there. There's a cross there. So you use your right hand, right? The thumb going in to the page or into the screen. Then your current is clockwise. That way. Right? So if you look at this part there, then it's a tangent going that way. So if due to this wire, then that is the direction of the field at this point there. Okay, remember they are all equal distance away. So the field strength will be the same at this point. Then you take this one going in also, right? The same, going in, use your finger there, going inside there. So it's curling clockwise. And then these two coming out, as we are using here, using A, coming out. Okay, so for as far as this one is concerned, this one is concerned, is going anti-clockwise. Right? So it's going that way. So that's why we get one going that way. Oh, sorry. We'll look at it again.
I don't understand the question. So.
Okay, this one is going in. So this one is your clockwise. Can you get the clockwise? Using your thumb, your right hand?
No.
The thumb going into the page?
No.
Can? Thumb going to the page? Your fingers? So it's going clockwise. At this point, it'll be a tangent to the curve, to the circle. Can get or not?
No.
Why cannot? What's the problem?
No, it's so tough, lah.
Where got tough? We are just using this. We are just using this one. Right? Your fingers represent the current. That one represent your magnetic field. So in this case, it's going anti-clockwise. That's all. So I just applying to here. Right? Just applying to here. Or thumb going into the page. So your fingers tell you it's going clockwise. Right? Clockwise. That's why it's clockwise. So the field at this point there is a tangent to the curve or tangent to the circle. So it means at this point there, it will still be the same as this direction. That's what we get. the strength to be smaller. And as you take this one as going into the page, right, you still be clockwise. So at this point there is going that way. That's what we get here. Right? These two vectors are the same magnitude because the distance is the same. That distance is the same. Then we look at this one. Right? The thumb is coming out. These two, the thumb is going in. Right? Thumb is going in. This one, the thumb is coming out. So the field is going that way. So it's anti-clockwise. Right? This one, anti-clockwise. So at this point, it's a tangent to the curve there. This one is a tangent to the curve there. Right? Same magnitude. Then we look at the final one. If it's coming out from here, right? It's the same. If it's coming out from here, this one is going up, like here, going up that way. So all these vectors add up. All these vectors add up. Right? Remember, they are equal length. They become a square. You complete your square to get the resultant. So the red one will be going that way. So that's why your answer is A. Can or not? Can or not? Okay, now we stop and start a new Zoom. Then we'll go over again. Yes or no? Yes or no?
Yes.
Okay, we'll take 10 minutes break. We'll take 5 minutes break and then we'll start a new Zoom. We won't take too long because I want you to understand first before we go to a new, before we stop for today. If not, no point in, I know the time 1 hour is over. I'm not going to charge you, don't worry. Okay, if no question to ask, we'll take 5 minutes break.